NAVEX, precise and scalable exploit generation approach for dynamic web applications. It is a joint work with Rigel Jomemo, Burhanu Ishit, and Venkat Venkatakrishnan. Modern web applications typically include many dynamic features that generate contents on the fly based on users. Based on user. Is that good? Yeah. Based on users' interactions and other inputs. Such dynamism improve the usability as well as the responsiveness of those applications to users. In addition to that, some tasks or functionalities, like for example, purchasing an item from an online shopping application, require a series of steps to accomplish. For example, viewing items, selecting some, adding them to a shopping cart, and then finally checking out. Usually, those steps are accomplished through different modules of the application, and there are strong dependencies between those interrelated modules. These characteristics, however, increase the application's complexity as well as raising the difficulty bar for analyzing the security of these applications. This is a simple online shopping application. It has three simple modules that represent its item purchasing logic. Let's assume that an attacker wants to exploit this application. He has first to find a vulnerability that can be exploited. Then he has to craft a malicious input for that vulnerability. And then the last thing is that he has to find a navigation path that will reach and triggers the vulnerability in that sink. This is a concrete exploit for a vulnerability, like let's say in checkout.php. This exploit is composed of 3 HTTP requests. Those HTTP requests will navigate the application from a public page, view.php, until the execution reaches the sink in checkout.php and exploits that vulnerability by sending that the malicious input in red. Constructing exploits automatically for large applications is challenging. The first reason is that usually large web applications consist of many modules, and there is a large number of intra-module execution paths in those applications. The second challenge is sink's reachability. What if a vulnerable sink that we want to generate an exploit for is located deep in this interrelated module structure? The solution is that the exploit has to navigate through those modules, and it has to satisfy the constraints required at each junction in this navigation path. As I mentioned before, web applications often contain features that are revealed only when the application is executed. These features include dynamically generated forms and links that may derive the navigation of the application to vulnerable sinks. The other challenge that we need to tackle is related to the goal of generating exploits automatically for different vulnerability types. We want to generate automatically exploits for injection vulnerabilities like SQL injection, file inclusion, code execution, as well as logic vulnerabilities like execution after redirect. And we want to achieve this goal with minimal changes to the analysis. So the goal of this work is to develop an automatic exploit generation approach that addresses all these challenges. Our main contribution is NAVEX, which is a system that scales the process of automatic exploit generation to large applications, and NAVEX identified over 200 exploits in modern web applications. At a high level, our approach combines static and dynamic analysis techniques to construct exploits. In particular, we find vulnerabilities in the code statically by analyzing the source code first, and then we build dynamically a graph that represents the navigation behavior of the application. And then we use that navigation graph and the identified vulnerabilities to find paths to those vulnerabilities. And a final exploit construction step is the last in our approach. We have implemented this approach in NAVEX. The input to the tool is the application source code and an attack dictionary. Basically, the attack dictionary has attack specifications for each vulnerability type that we are studying. These specifications basically contain lists of sinks, sanitizations, attack strings, and so on. We mainly use the attack dictionary to instantiate analysis templates for that targets all the vulnerability types that we want to generate exploits for. It is composed of two main steps, vulnerable sinks identification and the concrete exploits generation. In the first step, we create a model of individual modules of the application, and also we analyze each module in the application separately. The motivation for this is to address the scalability issues, the scalability challenges. By doing that, we prioritize only the modules. We prioritize the modules that have potentially exploitable vulnerability, and we further analyze them later. Our graph model of the code is based on code property graphs. Code property graph is a graph that combines different representations of the source code in one graph. Like, for example, the AST, the control flow graph, call graphs, and data dependency graphs are all combined in one graph called code property graph. We use this model to find vulnerabilities. And since our ultimate goal is not only to find vulnerabilities but to generate exploits, we've extended code property graph with two tags, sanitization and database constraint tags. Those tags are basically attributes that we use to to prioritize or to filter out a large number of potentially unexploitable paths. In the next step, we use that graph to find vulnerable paths between sources and sinks. And it's path-sensitive analysis. We have two graph traversal algorithms based on the vulnerability type that we want to find. For example, for injection vulnerabilities, we traverse data dependency edges in the enhanced code property graph backwards from sinks to sources. And while we are searching the graph, we utilize the tags to help us prune out potentially unexploitable paths. And then after we have all the vulnerable paths between sources and sinks, we construct formulas, and we use a constraint solver to basically solve those constraints and generate exploits only between from the source only that reaches the sink. The next step is to generate concrete exploits for the vulnerabilities that we identified. NAVEX executes several steps as shown in this figure. First, a dynamic execution component executes the application so that all the dynamic features or the dynamic code in the application is explicit. For that, we use a crawler that basically crawls the application and extracts links and forms. For all extracted links, we use those links as seeds for the next URLs to crawl. For forms, we should have support for input generation for those forms. And to do that, we automatically generate inputs for those forms by extracting, I'll explain that later, by extracting constraints from the form and generating inputs that will be accepted by the application automatically. And we also have support for generating inputs from JavaScript code that validates those forms. The JavaScript analysis part is based on a concurrent execution of one of our tools called NoTamper. We use all the crawled information, the links and the forms that we've generated inputs for to build the navigation graph. The navigation graph is a graph that represents the application, the whole application navigation. It's a directed graph. Nodes represent HTTP requests. Edges represent navigations between those nodes, either of type link or form. And then finally, we use this constructed navigation graph and the output of step 1 to find navigation paths to vulnerable sinks. This chart summarizes our automatic input generation for the client side for the forms. As I mentioned earlier, we extract formulas from the form input fields as well as the JavaScript code that validates this form. And we use a constraint solver to generate inputs that satisfy those constraints. We formulate an HTTP request based on those inputs that we got from the solver, and we feed that to the crawler. In the next step, we we utilize an execution tracing engine that generates traces while the application is execution. The goal behind this step is that when a user submits a form, the server-side code of the application usually enforces more constraints on the inputs that will be accepted by the application. So for that reason, we analyze the trace information that we got from the trace engine to check if the application accepted the inputs or not. If the application did not accept the form, we analyze that trace to extract the constraints from the server-side code, and we use a concurrent execution to derive formulas, and we feed that formula back to the solver, and so on until we successfully generate inputs that will be accepted by the application. NAVEX reports the locations of the vulnerable sinks using the information, using this information to search a navigation graph is not sufficient because of the file inclusion in web application. So, for example, if there is a vulnerability reported in checkout.php, and that file is included by another file in the navigation graph to search for a node that has a URL that matches checkout.php will fail. For this issue, we construct statically an inclusion map that will resolve the inclusion relationships so that when we search a navigation graph, we know exactly the destination URL that we should look for. If we want to search this is an example of a navigation graph. If we want to search a navigation path between the first and the second input, we got that from the first analysis step. If we want to search the navigation graph, one possible navigation path is between the nodes 2 to 6. And the URL for the destination, the URL of the destination node, we know that message parameter is vulnerable because we got that from the first analysis step. So what we do is that we replace that with the malicious input that we got from the first analysis step. And this is an exploit. This is the full exploit for that vulnerability. And as a result of our dynamic execution and the navigation graph design, the challenging problem of finding the navigation sequences between two modules is reduced to a simple graph search. The data, we've evaluated our tool on 26 web applications. With a total of 3.2 million source lines of PHP code. We've selected the data set contains popular and large applications such as WordPress and MediaWiki and Joomla. We've also selected older applications to compare our results with other state-of-the-art work. NAVEX constructed a total of 204 exploits. 195 of them are on logic vulnerabilities and 195 of them are on injection vulnerabilities, and the rest are on logic vulnerabilities. The enhanced code property graph reduced the false positive rate by 87%. And the client-side code analysis, when building the navigation graph, enhanced the precision by 54%. And we were able to drill down as deep as 6 HTTP requests to stitch an exploit. And this is a summary of the SQL injection exploits that we found, that the tool generated. reported 155 vulnerable things, and one constructed 105 concrete SQL injection exploits, and we've also generated 90 cross-site scripting exploits for those applications. For EAR vulnerability execution after redirect, we generated 9 EAR exploits for those applications. And we've measured the performance of NAVEX by calculating the total time to find all those vulnerabilities and to generate exploits. And the vulnerability identification time ranges from 17 to 109 minutes. And the exploit generation time ranges from 1 minute to 40 minutes. And this demonstrates that our tool can generate exploits that scales to large applications. And the figure below validates our claim that in order to to improve the crawling coverage and generate more exploits, we should have support for input generation and constraints extraction from client-side code. And to conclude, NAVEX is an automatic exploit generation system that considers the dynamic features of web applications as well as the navigation complexities. And we've constructed over 200 exploits, and NAVEX outperformed prior work on exploit generation. And our tool is on GitHub. Thank you.
Hi, Ben Stock from CISPA. Very interesting work. I was wondering about one thing about the analysis, the static analysis. How do you handle inter-procedure data flows? Especially if you have like a member of an object being invoked and you don't really know, unless you're running the code, what object that member belongs to.
Yeah, so there are two parts of your question. The inter-procedure, we have support for inter-procedure analysis because the code property graph includes call graphs. So we have that. The other part of your question is that do we have support for dynamic function calls? That part is not big. It's very challenging to resolve dynamic functions called statically. So for that, we inherit the limitations from code property graph. So we don't have support for the later part of your question.
Okay, but maybe just as a follow-up thought on this, you could also just look like in your namespace, which objects do define a function with that particular name. And since you do the pruning anyways, you can just branch back to both. Like let's say there's two functions with the same name, and you don't really know whether it's object 1 or object 2.
Yeah.
You can maybe branch to both. And then using your pruning techniques, you can maybe just say, okay, this can't really work because we have some constraints that can't be solved here.
We can't approximate that because we would not know which path to take unless the code is executed, right? Because those are.
But I'm saying just do both.
For all paths?
The question is how many paths are there? I have no idea. That would be an interesting question, whether you can just do like a shotgun approach and then prune using your techniques. But just
we'll have to examine that. Thank you.
Hey, Christian Steico from TU Darmstadt. I was wondering, can you say a bit more about the false positives? Since you have the crawler, I assume you could have just verified the exploit, right? So why do you have false positives?
Yeah. So the false positive is related to the first component, the static analysis. And for some of the, as I mentioned, for example, the dynamic function calls that we cannot resolve, we miss edges in the code property graph. So the tool reported that this is a vulnerable path, where in reality it's not. Those are false positives. So those are the cases that. The false positive, again, are reported for the first step, for the static analysis step.
I see. Thank you.
Mm-hmm.
My apologies if I missed this, but I was curious what your attack dictionary actually looks like.
Basically, the attack dictionary includes lists of things. Like, for example, for SQL injection, we have support for many types of PHP function calls that executes things, like MySQL query and so on. And it also includes sanitizations. And, like, for example, what are the good sanitization for SQL injection? And it also includes attack strings, like attack patterns. We collected those attack patterns from several sources. We use those attack patterns, we feed those attack patterns to the solver to generate the actual exploit. The attack dictionary also contains the two traversal types based on the vulnerability that we want to exploit. So let's say that we want to find a SQL injection vulnerability. We use all those stored information about the things that we need to search for, and then we use that during the graph search.
Okay, thank you.
Mm-hmm.
Great. Thanks very much, Abeer. Let's start with speakers.